Hey everyone, and welcome. Get ready to become a detective, because today we're investigating the incredible and sometimes mysterious world of changes that are happening all around us, all the time.
So let's start with a simple case. We see this all the time, right? You have a solid chunk of ice, you leave it out, and pretty soon you've got a puddle of water. It's an everyday puzzle, and we're going to solve it.
And then there's this one. You've got a shiny new iron nail, but if you leave it outside in the rain, it gets covered in this flaky, reddish-brown stuff. I mean, where did the shiny metal go? And what even is this new powder?
Or how about this classic transformation from the kitchen? You start with liquid milk, do a little bit of science, and suddenly it's thick, tangy curds, or even solid paneer. That's a total makeover.
So you have to wonder, are all these changes, melting ice, rusting nails, milk turning to curds, are they all the same? They seem so different. How can we possibly sort them out? Well, it turns out scientists use one single, super powerful question to solve this puzzle.
And this is it. This is the detective's master key. Every single time you see a change, all you have to ask yourself, is a new substance being made? Did the stuff I started with turn into completely new stuff? The answer to that one question unlocks everything. You see, that one question neatly divides every change into two main groups. First, you have a physical change. This is when the stuff is still the exact same thing, it just looks different. But then you have a chemical change, and that's when a real transformation happens. The stuff itself changes into something brand new. Okay, let's crack open our first case file. We're going to investigate physical changes, the masters of disguise, where the true identity of the substance never actually changes at all.
So here's the #1 rule for physical changes. No new substance is formed, ever. All we're doing is changing things like shape. When you tear paper, it's still paper, just in smaller bits. Or size. When you crush chalk, it's still chalk, just a powder. Or state. When ice melts into water, it's still H2O. And a big clue is that these changes are usually temporary, and you can reverse them. Now, this is a classic trap where a lot of people get confused. You dissolve sugar in water, and it completely vanishes. It looks like it's gone forever. So that must be a chemical change, right? Well, let's investigate the evidence. Let's walk through the clues together. You stir the sugar in, and it seems to disappear. But, and here's the key piece of evidence, if you taste the water, it's sweet. That sweetness is a property of sugar. It proves the sugar is still there, it's just broken up into tiny particles spread all through the water. Since no new substance was made, dissolving is a physical change. Case closed.
All right, time to open our second case file. This is where things get really transformative. We're talking about chemical changes, where you end up with completely new stuff.
So how do you spot one of these? You look for clues. If you see fizzing or bubbles, that means a new gas is being made. If it gives off heat or light, like a fire, that's a huge sign. A permanent change in color, like our rusty nail, is another dead giveaway. Or maybe there's a new smell, or a new solid suddenly appears in a liquid. These are all signs a chemical change has happened. Now, the proper science term for this whole process is a chemical reaction, and the vocabulary is pretty simple. The original ingredients you start with are called the reactants, and the brand new substances that are formed at the end, those are the products. It's that simple. Reactants react to form products. A perfect example is the classic baking soda and vinegar experiment. You mix them together, and what happens? Instant fizzing. You've got bubbles, which is our clue that a gas is being produced. That gas is a brand new substance called carbon dioxide that wasn't there before. And you can prove it's a new gas because if you bubble it through lime water, the lime water turns milky. Another really cool thing about chemical reactions is that they always involve energy. They either release it or they absorb it. If a reaction releases energy, we call it exothermic. It feels hot, like burning wood. If a reaction has to absorb energy to happen, it's called endothermic, and it might even make its surroundings feel cold. One of the most famous exothermic reactions is something called combustion. Now, that sounds like a big fancy word, but it's really just the scientific name for burning. It's a super fast chemical change where something reacts with oxygen to produce a whole lot of heat and light. And for burning to happen, you absolutely need 3 things. We call it the fire triangle. First, you need fuel, the stuff that burns. Second, you need a supporter, which is almost always oxygen from the air. And third, you need enough heat to get it all started. If you take away any one of those 3 things, the fire goes out.
Okay, detective, time for a master level case. Let's apply everything we've learned to a burning candle. It seems simple, but there's a really cool twist here that makes it a bit trickier than it looks. Here's the secret. A burning candle is an amazing example because it has both types of change happening at once. First, there's a physical change. The heat from the flame melts the solid wax into liquid wax. Same stuff, just a different state. But then, that liquid wax travels up the wick and gets hot enough to turn into a gas. And that's when the chemical change happens. The wax vapor burns, that's combustion, and creates totally new things. So you see, both changes working together. This brings us to another really useful clue, reversibility. Most physical changes can be undone. You can freeze that melted water right back into ice. But most chemical changes are irreversible. You just can't unburn a piece of paper, right? And you can't unrust a nail. So if a change is pretty much permanent, there's a very good chance it's chemical. So we've cracked the case. We know how to tell physical and chemical changes apart. But you might be wondering, so what? Why does this actually matter in real life? Well, it turns out it matters a whole lot. Understanding this stuff is everywhere. Cooking is all about chemical changes. Knowing rusting is a chemical change is exactly why we paint our bikes and gates, to stop it from happening. All the amazing medicines and materials we use are thanks to scientists controlling chemical changes. This knowledge is basically a superpower for understanding the world. So, the world is now your laboratory. You have the master key, that one critical question, and you have your list of clues. From what's happening in your kitchen to what you see in the park, changes are going on everywhere. Now that you're a change detective, what mystery will you solve next?